Hello all. I just decided to make a summary about the light absorption and transmittance in 2 slides you'll see. So as you may remember from the theoretical courses and from the lab, the concentration of the material was our purpose to determine. And to make it visible, I just picked a sample which is colorful, as you can see. On the slide at the top, we have a sample which is blue in color. And as you can visually see, when the concentration of the material is higher, we see a darker color. So the sample on the left, this one. Okay, I'll try to right now. So this one has the highest concentration, and the one on the right, which is this one, has the lowest concentration. We can just make some numbers about them. For example, let's imagine this one is 10, this one is 8, this one is 6, this one is 4, 2. And we can also make up some units. It can be milligram per liter, for example. It can be any concentration unit. So what we see is with the increasing of concentration of material in our sample, the color is getting darker. And that was the change we can observe and determine the concentration by light-matter interaction, which was absorption transmittance. And as you can remember, we were using some light source. So there is a bulb, and the light with a high intensity, which means quite big number of photons, is sent to the sample. And in the sample holder, depending on the concentration and of course the wavelength of the radiation, the light can be absorbed or it can be transmitted. The transmitted portion is shown here. So some of the light is absorbed by the material, some of the light is transmitted. And it's quite clear if you have a high matter concentration like this one, most of the light will be absorbed and the transmitted portion will be less. And if we prepare these samples with known concentrations, starting from 2 milligram per liter, going up to 10 milligram per liter, we just made the numbers and units. And if we just measure the absorbed portion of the light, the absorbance, in other words, we can just plot the calibration curve. Calibration curve was giving us the relationship between the concentration versus the signal. The signal we observe is absorbance, and the concentration is at the x-axis for the calibration curve, so it should be like this: 2, 4, 6, 8, 10 milligram per liter with respect to the units numbers we just made. So if I measure the absorbance for these known concentrations, I can find the data like this. And if I just plot a line which is fitting as good as it gets, I mean, to these data points, you will get the hopefully linear or nicely fitting the calibration curve, which will have equation like slope times x plus n. Here x is the concentration, m is the slope of the line, and y is the absorbance value. So what we have found here, we just prepared our samples with known concentrations, and we measured the absorbance value So we find a relationship between absorbance and concentration. And if I just receive a sample with an unknown concentration, I can measure the absorbance of that sample. It can be something like this value, for example. And if unknown sample has this absorbance, I can just go to my calibration curve line, which is the showing us the relationship between absorbance and concentration. If I just go like this, I can read or find out the concentration of the unknown sample. So I guess this part is clear. If we have a high concentration of material, the light will be much more absorbed because there is much more material to absorb the light. So the concentration is related with the absorbed amount of light. Please remember that the light can be infrared, or it can be visible light or UV. And we have seen different instruments working with different types of light. Let's clear it out and we may proceed to HPLC. So in HPLC, as you may remember, the results was given as in the form of chromatogram. It was showing us the retention time for different components in our sample. Sample is with some components. So we are just separating these components by using the column and the interaction of material or components with the stationary phase in the column. We were just doing the separation. That's why we were receiving components at different retention times. And after separation, the components, separated components, were sent to the detectors. So there could be different types of detectors. One of the detectors was like the diode array detector, which was quite like the visible spectrophotometer. Again, we are just observing the light absorbance or transmittance. And as we just discussed in the first slide, if the material concentration is high, there will be a higher absorbance of light. And if there's a higher absorbance of light, you will see a high intensity or high signal, which means you will have a bigger peak. So the concentration is related with the peak size. For the peak size, in fact, we are determining the peak area. So as you may remember, this area was important. And if you have a larger area, it means you have a higher concentration of component F, for example. So we can do the same thing, the calibration curve preparation, as we just discussed in the first slide. We can prepare samples with known concentrations, and we can just inject it to the HPLC and check the area under the curve, this area, for different concentrations. And we can just prepare our calibration curve again, which is showing us the relationship between concentration versus the area under the peak. So if we have again a sample with unknown concentration, I can inject it to the HPLC, find the area. So imagine this is my unknown sample and its area is with this value. I can again use the calibration curve to find the concentration of my unknown sample. Um, I tried to explain the fundamental logic of the absorption transmittance and how we use it for different devices, basically for HPLC as well. And about the transmittance and absorption, we were using the equations given here. The transmittance was the ratio of the intensity over the initial intensity. And absorption was defined as the logarithm of 1 over t. So if someone says we have a transmittance value of 20%, for example, you should be writing it like this. So the transmittance 0.2. And in these equations, for example, for this one, you will be writing 1 over O2, not 20, but if it's 20%, you should be writing the transmittance is equal to 0.2. Similar for absorption, if someone says the absorbance is 30%, it means it's 0.3 or 0.30. Again, the equations you should be using the value in this form. Well, that was just a small summary to make it somehow clear, the absorbance and transmittance and the equations and the numerical values, how to put them in equations so you can make the calculations by yourself. And I just tried to remind you about what's the calibration curve, why it is important, and how we use it. And in the advanced instruments, the calibration curve is somehow defined to the software, like the spectrophotometer or HPLC. So the instrument holds the information about the calibration curve itself, and when you inject or when you just supply a new data of unknown sample, it calculates the concentration and tells you immediately by using the calibration curve itself. Well, I hope the information is somehow helpful to you, and please don't hesitate to ask questions if you have any, whenever you like. Well, I wish you have a nice day then.